Alright guys, so today we are looking at probability. Nice thing about probability, there is no definitions, there's no basic, necessary information. Probability is all about common sense and looking at all of your options. So I know you've done basic probability in Algebra 1. We're going to do some basic, that's what we're starting with. We'll move up to some of the harder problems. Let's look at example 1. You are spinning the wheel that I have shown. Simply find the following probabilities. We want to know what's the probability of spinning a 6. Well, if you look at this wheel, there is 1 6 on the wheel, and there are 8 possibilities. Probability is simply found by writing a fraction. The number of items that you want goes on top. There was 1 6. The total number of possibilities, which was 8, goes on the bottom. That's probability. However, one requirement always is that every fraction is reduced. 1/8 is definitely reduced. We're done there. Problem B, spinning a number greater than 5. So there's my fraction bar. Numbers greater than 5 would be 6, 7, and 8. So that is three possibilities. Again, out of a total of 8. Is 3/8 reduced? Yes, it is. You move on. Spinning an even number. Well, even numbers are 2, 4, 6, and 8. So there are 4 possibilities out of the 8. That is not reduced. 4 out of 8. Both of those can be reduced by 4. Reduces down to 1/2. So, as I said, those are very basic probabilities, just to get your brain kind of thinking. Example 2, also meant to be very basics. The graph you see here shows how many students are enrolled in Algebra 1, Geometry, Algebra 2, and NAMS. You are randomly selecting one student. Find the following probabilities. What's the probability of the students in NAMS? What's the probability that a student is in Algebra 1 or Algebra 2? Notice one difference between this problem and the pie problem, the spinner. We don't know a total here. We have a bar graph. So the first thing we need to do is we need to find a total. And of course the total is found by adding up how many students there are. So 87 and 69 and 72 and 15. If you type all that in your calculator, you get a total of 243. Now that we have a total, we can find our probabilities. NAMS, if we look at our bar graph, there are 15 students in NAMS. That goes on top. The bottom is, again, the total, 243. These might be a little tougher to simplify. Both of these are divisible by 3, and it reduces to 5/81. I highly suggest, if you have a scientific calculator, bring it to class. I can show you how to reduce on your calculators. Cell phone calculators do not do the reducing. You have to do it on your own. B, probability of Algebra 1 or Algebra 2. Well, here's Algebra 1 and here's Algebra 2. So those two groups combined, 87 plus 72 is 159. So we have 159 over 243 total. These are both, again, divisible by 3, and that leaves me with 53/81. So, again, a basic example. The difference was we had to find the total before we could go any further. Go ahead, guys. Turn the page. One of the most common questions dealing with probability deals with cards. And so I never like to make the assumption that you know a standard deck of playing cards. So this is a deck of cards. As you can see, we have black cards and red cards. We have aces all the way up to kings. The one question they do ask about are the suits. Those are the little shapes on the cards. If you don't know them, you might want to jot these down. The top ones here, these are clubs. The next row down, these are spades. Third row, obviously, hearts. Bottom row, diamonds. So make sure if you don't know the names of them in your notes, get those jotted down. because example 3, and then there's several later examples, refer to your deck of cards. If you need to constantly look back at your cards, please look back, take a look at what you need to know. But I'm going to turn to example 3. You're drawing one card from a standard deck of 52 cards. That's how many cards that we just saw were 52. Find the following probabilities. Probability of a 5. Well, if we look, there are 1, 2, 3, 4 5s. So 4 out of 52. Those can both be divided by 4. You get 1 out of 13. Probability of a heart. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts out of 52 total cards. Now you may think that this is not reducible. However, these can both be divided by 13 and you get a fraction of 1 over 4. Probability of a face card. These have to have a face on them. Aces and tens are not face cards. These, the Jack, King, and Queen, all have faces. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 12 out of 52. These can both be divided by 4. We end up with 3 out of 13. Finally, not an 8. Well, if we look, there are 1, 2, 3, 4 8s in the deck. So everything else is not an 8. So that means that there are 48 cards that are not 8s out of 52. These are also both divisible by by 4, and you get 12 out of 13. So we're going to pause for a second. These have been your basic examples. These are the ones that are very just common sense. Can you count? Can you reduce? We're going to look now at a couple of words that are very important in probability. The first word that they like to mention is the word and. They like to talk about two things happening. And the word and can also sometimes be interchanged, see and here, with then. And then both mean exactly the same thing. Very easy. If you want to find the probability of A and B, as you can see right here, all you do is find the probability of A, find the probability of B, and multiply. And then simply mean multiply your fractions. So on these, we're going to be finding two fractions, and we're simply going to multiply the results. So, just remember, and then means multiply. Also, we have another word that comes up in probability. That is the word or. Let me get rid of that ugly purple color. There we go. Or is a little trickier because or, there can be overlap going on. There are two different kinds of ors. There are ors where there is no overlap. That would be this first equation. If the two things that we are referring to do not have anything in common, all you have to do is add the two probabilities together. However, if the two items still say or, but there is things in common, you still add the probabilities together, but you have to subtract how many they have in common. And the easiest way to explain the ors are when we get to an example, which will be example 5. So we're going to look at example 4 first. These are your then problems. So then and mean multiply, or means add. So let's take a look at some examples. You are rolling a die, yes, die is singular for dice, twice. Find the following probabilities. Well, when we roll a die, I'm going to hope that you know what a die looks like. For those of you that don't, the only numbers that you're going to get are 1, 2, 3, 4, 5, and 6. We can use that as a reference when we're trying to answer these questions. So as you notice, probability of 4, then 3. So let's start with 4. If I'm trying to get a 4 from these numbers, there is 1 4 in the group and 6 numbers total. 3, there is 1 3 in the group, 6 numbers total. Then means multiply. I'm going to multiply the tops. I get 1. Multiply the bottoms. I get 36. That cannot be reduced. Let's look at the next one. Probability of 5. So that there's only 1 5 out of 6 numbers. Probability of an odd. Well, odds are 1, 3, and 5. So there are 3 of them out of 6. And we're still multiplying because it's still then. The tops are 3. The bottoms are 36. These are both divisible by 3. So we get 1 over 12. Let's look at the last one. Probability of 2, and then 7. Well, there is 1 2 up there out of 6 numbers. However, there are no 7s up there. So 0 out of 6. When we multiply, we get 0 out of 6, which is just 0. When something cannot happen, in other words, it's impossible, the probability is always 0. All right, so let's look at some that are going to be your OR problems. These are a little more complicated. This is really where your deck of cards is going to come in handy because we're using our deck of cards again. You're playing with a standard deck of 52 cards. You select one card at random. Find the following probabilities. So, first thing we're looking at is the probability of 3 or 6. So let's refer to our cards. Let's go back to our deck, focusing on 3s first. If we look at our deck of cards, we have 1, 2, 3, 4 3s out of 52 cards. Or means add. Now let's look at our 6s. 1, 2, 3, 4 6s. Also out of 52. Here's the big question. If I look at my deck, did I point at any of the cards more than once? And the answer is no. The 3s were over here. The 6s were over here. There are no cards that were overlapping. This is a problem where after you add, you're ready to find the answer. 4 plus 4 is 8. Don't change the denominator. This isn't multiplying. Both of those are divisible by 4. We get 2 out of 13. Let's look at the next one. Hearts or clubs? Start with hearts. This would be the third row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts. Out of 52. Plus, because it's or, we're looking for clubs. That would be the top row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Also out of 52. If you look back at our cards, were there any cards that had both a heart and a club on it? No. The first were all the third row. The other fraction was all the top row. There was no overlap there. So we are ready to find our answer. And that would be 26 out of 52. These are both divisible by 26. You get 1 out of 2. These next two, we're going to pay a little more close attention to. Let's start with the probability of an ace or a diamond. So our aces, they are right here. There are a total of 1, 2, 3, 4 of them out of 52, plus diamonds. sorry, wrong way. We are looking at this whole bottom row. There are 13 diamonds. This one, however, I want to point out, if you notice, this ace of diamonds here, he was circled both times. You can't count a card 2 times. So there is one card that was both an ace and a diamond. So we're going to subtract off that one card out of 52. So 4 plus 13 is 17. Take away 1 is 16 out of 52. These are both divisible by 4. You get 4 out of 13. Pause real quick. I want you guys to try part D before we keep going. I want you to try one on your own. All right, hopefully at this point you've tried this one on your own. Let's take a look for our spades. So first I'm going to clear all this out. All right, so our spades are this row right here. We have a total of 13 in that row out of 52. Or means add face cards. Those were the guys with the faces. That was that group right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them out of 52. But if you notice, these 3 right here were counted in both groups. The Jack, Queen, and King of Spades have both spades and faces. So we are going to subtract 3 out of 52. 13 plus 12 is 25, and 25 take away 3 is 22 out of 52. Those can both be reduced by 2, and you get 11 out of 26. So that's kind of the end of the basic probability. We're going to take a look now at some other vocab words that come along with probability. First vocab word is sample space. The sample space is simply a list of all of the possible outcomes of an event. When we did the problem with the dice and I listed out the numbers 1 through 6, that was an example of a sample space. It helped us answer the questions that we needed to answer. A tree diagram. This is a diagram using what we call branches to show all of the possible outcomes of a situation. These can be used to help list the sample space. It's kind of a way of organizing your work. We'll do a couple of these so you can see what I mean. The fundamental counting principle. If one event E has N outcomes and another event F has M outcomes, then if I ask you to do E and F together, they have M times N outcomes. So you simply take the number of outcomes of each event and you multiply them together. Very, very easy. So what we're going to do now is we're going to use these definitions. We're going to do some sample space. We're going to do some outcomes. We're going to use a little of all of these. So let's start with the very basics. Sample space. We are listing the sample space for these 3 problems. First one's pretty easy. You're rolling a die. You have one die in your hand. You roll it. What are all the sides of the die? They are 1, 2, 3, 4, 5, and 6. You are expected to make a full list. You cannot say 1 through 6. You have to list them out. Let's look at this next one. Flipping 2 coins. This is where a tree diagram can come in handy. If I take my first coin and I flip it, the only options I have are heads and tails, which, by the way, in math, we use H and T. So I'm going to write down those options. H, T. However, I'm flipping a second coin. Well, depending upon what happens on the first one, the second one I can still get an H and T. So on the first one, if I get a head, the second one, there's my branches, I could get a head or a tail. On my tail here, my second coin could also be a head or a tail. And so using the branches, you can then write your sample space. So I could get a head and a head. That's one possibility. I could get a head, then a tail. I could get a tail, then a head. I could get a tail, then a tail. So as you can see, making one of these tree diagrams, which are not difficult, helps you write out the sample space and you don't forget any options in the process. Let's look at the next one, rolling a die and flipping a coin. Let's talk about rolling the die. We already looked at A. Rolling a die, you have 1 through 6. So I'm going to write those out. 1, 2, 3, 4, 5, 6. However, that's not all we're doing. We are also flipping a coin. So when I roll a 1, my coin could still say H or T. When I roll a 2, my coin can still say H or T. Same thing all the way down the line. So make your tree with H and T for each number. So now my sample space would be a 1 and an H, then a 1 and a T, then a 2 and an H, then a 2 and a T, and so on and so forth. So go ahead, as you can see, I'm finishing that list. So that is the idea of actually finding sample space. If you just draw a tree diagram, that is not sufficient. The tree diagram is only to help you write out the list, and lists have commas. Let's take a look at the next example. Determine how many outcomes are possible. We are not concerned with what are the outcomes. We simply want to know how many are there. So you have a family, you're trying to find out how many different outcomes are possible for the gender of the children of a family of 3. So you have 3 children. This is where I use little blanks again, child 1, child 2, child 3. Well, child 1 could have either been a boy or a girl. You have 2 options there. Child 2 could either be a boy or a girl. Again, 2 options there. Child 3 could be a boy or a girl. 2 options there. And this, when you are trying to combine all 3 together, this is that fundamental counting principle. You multiply all the options. 2 times 2 times 2 is 8. You are flipping a coin 5 times. So 5 flips. 1, 2, 3, 4, 5 flips. The first flip, 2 options, heads or tails. Second flip, still 2 options. Same thing with the third, and the fourth, and the fifth. You can't get rid of one of those options because a coin, you can't change a coin. When you multiply, you get 32 options. Now, you have a marble, you are drawing a marble from a bag of 12 marbles. The problem is you are not replacing that marble. So you're going to take a marble out, you're going to set it down, the bag is now changed. You're then drawing a second marble. So first draw, second draw. First draw, there's 12 marbles in the bag. However, you took a marble out and you left it out. So on that second draw, there's only 11 marbles in the bag. And so when we multiply those, we get 132. So these are very easy questions. They like to ask these on the EOC. How many options are possible? Just think, when they say how many options are possible, you're multiplying things together. So let's look at our next big application problem. You are listing the sample space for rolling 2 dice. One is red, one is white. So your first die, you have the numbers 1 through 6. The second die, you also have the numbers 1 through 6. We're pairing them together and listing every option. I do this systematically. The first die is not going to change. It's going to stay 1 the whole time. So 1 gets rolled all the way down. However, the white die is changing. So a 1 on the red can go with a 1 on the white. A 1 on the red can go with a 2 on the white. 1 on the red can go with a 3. 1 goes with 4. 1 goes with 5. 1 goes with 6. That's your systematic way of doing this. Now, the red die changes to obviously, 2. And the white die goes through its numbers again. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. The pattern continues. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. Notice there's a lot of them. This list right here will be helpful on our next set of examples though. Whoops, not 3. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So as you can see, there's 36 possibilities here when you roll 2 dice. And so we are going to use this list of 36 possibilities to answer problem 7. So let's take a look. I'm sorry, this is example 9. Use the sample space to find the following probabilities. The sum of 8. As we've already decided, there's 36 total possibilities. We need to look through our list and find out which pairs add up to 8. So, nothing in the first row does. In the second row, it looks like we have 2 and 6. Third row looks like we have 3 and 5. Fourth row looks like we have 4 and 4. Then 5 and 3. Then 6 and 2. Do you notice they're on a diagonal? That's not a coincidence. There are a total of 1, 2, 3, 4, 5 ways to get 36. And that cannot be reduced. A sum of, whoops, that should say of 3 or, there's a key word. We know or means add them up, 3 or 6. So we're looking for 3's first. I look down the first list, there's a 3. No more. Look down the second list, there's a 3. And then the rest of them start off too high. So we have 2 out of 36. We are adding that 6's. First list, do we have any 6's? Looks like right here. Second list, I like a little plus next to it. 2 and 4. Moving up the diagonal, 3 and 3. Diagonal 4 and 2. Diagonal 5 and 1. So it looks like we have 1, 2, 3, 4, 5 possibilities. When we add those up, we get 7 out of 36. Finally, we have the sum greater than 8. So greater than 8 is 9 and higher. So we're talking about 9, 10, 11, and 12. So if you want, you can start finding all of them at one time. Let's look for the lowest possibility we have is 9. So the first row, none of those make 9s. The next one, none of those make 9s. Third one, there's a 9. Fourth one, there's a 9, there's a 10. Fifth one, going the diagonal, 9, 10, and 11. Last one, 9, 10, 11, and 12. So if you look at my highlighted ones, there is a total, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like there's 10 of them. So we're talking about 10 out of 36. Those can both be divided by 2. So we have 5 out of 18. All right, we have 2 last examples, guys. We're getting there. I know this is a longer one. 3 cards are drawn from a deck of cards, and keyword here, not replaced. You are changing your deck of cards every time. So we are looking at the probability of getting 3 jacks. So another way of writing that is a jack, then a jack, then a jack. So we're going to be using our deck of cards again. Notice the word then. If you look through all of 3 of these examples, we have the word then. We are multiplying. Now this, your calculator is not going to like as much because we're going to get some big numbers. We have 3 fractions that are being multiplied. Let's start with a jack. So as you can see, we have 1, 2, 3, 4 jacks in our deck out of 52 cards. But here's the deal. We drew a jack out and it's gone. So I am going to blacken out that jack. He's gone. Now for our next choice, we only have 3 jacks left. But in addition, we only have 51 cards now. So 3 jacks are now left, 51 total cards are now left. So we just pulled another jack. That's gone. We now have 2 jacks left and 50 cards. Now here's the problem. If you multiply the tops together and you multiply the bottoms together, you're going to have some massive numbers. Your calculators are not going to reduce those. You're going to have to do a little bit of the old-fashioned canceling before you multiply. Let me show you what I mean. For instance, 2 and 50 can both be divided by 2. You're left with a 1 and a 25. 4 and 52 can both be divided by 4. You're left with a 1 and a 13. 3 and 51 can both be divided by 3. You're left with a 1 and a 17. Now that you're done with all your reducing, there's 1s on the tops. Now you don't got to worry about it later. So if we multiply the tops, 1 times 1 times 1 is 1, and 13 times 17 times 25 is 5,525. So that was a little different. Let's do the next one. New deck of cards. I'm taking away all the cards that I took out, they're going back in. We're talking about an ace, then a king, then another ace. So let's clear. All the cards are back in. So we're looking at an ace. So as you can see, we have 4 aces. So I'm going to come over here and say 4 out of 52. However, we took an ace out. So let me blacken one of my aces. I now am trying to find a king. So as you can see, there are still 4 kings in the deck. However, since we took an ace out, there's only 51 cards in the deck. So 4 kings out of 51 cards. Now, we're going to blacken a king. Finally, I'm trying to find another ace. Well, as you can see, there's 3 aces still left, but we're down to 50 cards. So 3 out of 50. Now we're going to do some reducing. Just like before, 4 and 52, both divide by 4. You're left with 1 and 13. This time we got to go diagonal. 3 and 51 cancel and leave you with a 1 and a 13. 4 and 50 are both divisible by 2. Oh, I'm sorry, I made a mistake. That should be a 17. 4 and 50 are both divisible by 2. That leaves us with a 2 up here and a 25 down there. If you look, there's no more reducing we can do. Multiply the tops, you get 2. Multiply the bottoms, you get 5,525. So now I want you guys to pause the video, try this next one. Remember, if you've been crossing off your deck like I have, your deck is back to normal. So now you are trying to find a club then a spade, then a spade. So go ahead and pause the video and try this one. When you start it back up, you'll see the answer. Alrighty, so let's see how you did. So let's start with a club. That's this top group of guys. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 clubs out of 52 cards. Problem is, a club is now gone. And no, it doesn't matter which one. Then, we're talking about a spade. This is the next row down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spades. However, there's only 51 cards left. Then, we take out a spade. So we blacken one of those spades. Now we're trying to find another spade. So now we only have 12 spades, and we are down to 50 cards. So 12 out of 50. This one, we got to be a little more cautious with our canceling. 13 and 52 are both divisible by 13. That leaves us with a 1 and a 4. If we look, we know, and there's several ways of doing this, I know 4 and 12 can be reduced. 4 and 12 can both be divided by 4. That leaves me with a 1 down here and a 3 over here. I know, just from example A, that 3 and 51 can both be reduced by 3. So we're left with a 1 and a 17. If we look at what we have left, we have a 1 and a 13 and a 1. That's all the reducing we can do. So 1 times 13 times 1 is 13. And 1 times 17 times 50 is 850. And that is all the reducing that you can do. Hopefully you got that answer right. We're down to our last example. I know, long list. This is an easy one. This table shows the probability for 911 calls each hour in a town. So it shows how many calls per hour and the probability. We are simply trying to find the probability that there were less than 4 calls. Less than, whoops, let's get rid of that ugly color. Less than 4. So less than 4 is 3, 2, and 1, and 0. So all we're doing is we're taking the answers for 3, 2, 1, and 0. That would be these guys right here. And we're adding them up. Super easy. 0.21 plus 0.30 plus 0.18 plus 0.13. And you should get 0.82. Super easy, right? Okay, so pause. I want you to try B and C on your own. Then unpause and you will see the answers. Okay, so this next one, at least 6 calls. When I say at least 6, at least means 6 or more, which means the numbers 6 and 7 for us. So we're looking at those two right there. So 0.03 plus 0.01 is 0.04. And then finally, 5 or fewer. So 5 is included or fewer. So 5, 4, 3, 2, 1, and 0. So we're looking at this big group right there. So we're talking about 0.21 and 0.30 and 0.18 and 0.13 and 0.09 and 0.05. When you add all that up, you get 0.96. So I know it was a long lesson, but that was a really easy way to finish that long lesson. So hopefully you are now ready to at least get a start on your homework. That way, when you come to class, you still have time to finish, but you've gotten a head start on it.